So in our original limit, we will go in and instead of writing xy goes to 0, we'll look at r going to 0 from the right. We'll replace xy with r cosine theta and r sine theta. That'll give us r squared cosine of theta sine of theta. And in the denominator, when we replace x squared plus y squared, we have our identity that tells us that we'll have instead the square root of r squared. So simplifying this, we still have our limit as r goes to 0 from the right of r squared cosine of theta sine of theta all over r. Square root of r squared is r. Then we'll get some simplification here. This r in the denominator will cancel out with the 1 in the numerator. And at this point, we could probably go ahead and take our limit. Remember, cosine of theta and sine of theta they don't have a variable that we're interested in because theta just takes us on a sinusoidal curve. But r is going to go to 0. So as r goes to 0, this is going to give us a whole big fat 0. And 0 happens to be the value of g of 0, 0. So what we've done is we've shown that the limit of our function as x and y go to 0, 0 is equal to 0, which is also equal to the function value. So therefore, we can say that g of xy is continuous on all of R2. So in other words, on our two-dimensional plane. All right. So in this next problem, we're asked, where is the given function continuous? And we're told that f of xy is equal to x squared minus y squared, all divided by x squared plus y squared. And if we want to know where it's continuous on its domain, we don't necessarily need to go through the whole rigmarole of taking a limit and whatnot. What we need to figure out is, where is it not defined? Okay, because if we can figure out where this is not defined, then those places where there's lack of definition could be where there's a vertical asymptote or a hole or something like that. Since we're working with a rational equation, in other words, a fraction, our only issues are going to come from the denominator. So if our denominator is equal to 0, there's going to be problems. So we'll write that. If the denominator is 0, and the particular issue that comes up is that there is a vertical asymptote. Okay, so there's an issue there. We don't have continuity. So if we want to state where our given function is continuous, we would say that it is continuous on its domain. And that domain is the set of all xy pairs such that x squared plus y squared cannot be 0. And that's it. That's how we answer the question. The next problem has a little bit more to it, mainly because it is a piecewise function, and so the place where there may be lack of definition is made up for by the second piece. Okay, so we're going to go through our steps here. In here, we're told to determine the domain of continuity of the function f of xy, which is piecewise. The first piece is xy, all divided by x squared plus xy plus y squared, and that's if our xy pairs are not equal to 0, 0. And the second piece, f of xy is equal to 0 if our ordered pair xy is equal to 0, 0. So let's examine that first piece. In the first piece, xy over x squared plus xy plus y squared is continuous on the set of xy pairs such that x squared plus xy plus y squared does not equal 0. And now we want to see, is the limit as x and y approaches 0, 0 going to be equal to 0? Because we would need the limit to equal 0, which would equal the function value. So we need to see if the limit as xy approaches 0, 0 of xy over x squared plus xy plus y squared Is this equal to f of 0, 0, which as we see from the second piece is equal to 0? All right, just looking at this, I can imagine plugging in the values x is 0 and y is 0, and I'm going to get 0 over 0. So direct substitution will not work. The denominator does not factor. Nothing's going to simplify nicely for us. So our only course of action is to start checking paths. So let's check paths. And I'll start with along x is equal to 0, which is the y-axis. So I'm going to look at my function. F of 0y would be equal to, well, if I replace all x's with 0, I end up with 0 in the numerator and y squared in the denominator. And 0 over y squared is 0. So what this means is that f goes to 0 as y goes to 0 in that equation. The next path would be along the x-axis where y is equal to 0. So now we're going to examine f of x comma 0. Plugging in 0 for y everywhere in my function, I get a 0 in the numerator and x squared in the denominator. 0 over anything is still 0. So I could say that f goes to 0 as x goes to 0. I'm going to try another path. Let's try y equals x. That's always a good third path. So here I'm going to replace all y's with x, and I get f of xx is equal to, everywhere there's a y, I'll replace it with an x. I get an x squared, or an x times x on top. I get an x squared plus x times x plus an x squared. This is going to simplify to be x squared over 3x squared, which is just 1/3. So what this means is that f is going to 1/3 as x goes to 0. We got two different limiting values, and they were path dependent. So what we can say here is that getting 0 and 1/3 as limit values means we don't have one unique limit. The limit is path dependent. So it just depends what direction we're coming from. And so therefore, the limit does not exist at 0, 0. And f of xy is continuous on the set of all xy values such that the ordered pair xy just cannot be 0, 0. Because at 0, 0 we had issues. So even though the limit, even though the second piece gives us a definition of the function, we didn't have that the limit was equal to that value of the function. So that's why we can say that the limit does not exist. I hope this clears things up. For continuity and limits, please reach out if you have any questions at all.